Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, and a very good day. Okay, so I'm not sure when you watching this video. So first of all, I would like to apologize that I couldn't do this week class live online. So I've made this pre-recorded video. So I hope that you listen to my lecture. And if you have any questions, if you don't understand anything, you can always WhatsApp or email to me. I'm always available, inshallah. It's just that I can't do a live online class for this week. Okay, so let's start. Okay, last week we have I have introduced to you the concept of thermodynamics. So what is the difference between thermodynamics and aerothermodynamics? Not actually the difference. So what is the extra value of aerothermodynamics and why we need to learn aerothermodynamics for aerospace engineers. Okay, so we have seen what we have learned last week. The definition of energy, the steady flow, dimension SI units, and then about closed system, open system, right? Okay, so today, chapter 2, the new chapter, is still about basic of thermodynamics. And plus, this chapter consists also, I think, some of the parts in this chapter you have we have learned in fluid mechanics. Somehow related to fluid mechanics, okay? So maybe some of the slides I'm not going to go into detail because I hope and I think you have seen them in fluid mechanics, okay? Okay, so we start. So this chapter is called thermodynamics principles. Okay, still like fundamental part. Chapter 2. So these are the content of this chapter. Okay, so we see later on the objective of this chapter. Also, we can pass. Okay, so actually this chapter is all about temperature and pressure. Temperature and pressure. At least you have to understand these two properties first. Okay, these two properties, temperature and pressure, are the most important properties. We have others properties also, mass flow rate, energy, etc. But these two properties, temperature and pressure, are the most used in thermodynamics. Okay, means that whatever other property, physical properties that we are going to learn in the future is actually based on these two properties, temperature, pressure. Okay, so temperature and the zeroth law of thermodynamics. Okay, last week I mentioned that we have first law and second law of thermodynamics that you are going to learn in this aerothermodynamic course. But we also have zero, zeroth law. It's a bit janggal. Yeah, it's a bit different. Zeroth law. Yeah, we thought that we only have first and second, but we have zero. Okay, but we don't have negative law. Okay, thankfully. So we have zeroth law of thermodynamics. Okay, zeroth law of thermodynamics. So what does this law say? If two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. What does it mean? Okay, it means that two bodies, for example here, iron and copper. Okay, these two bodies, we said that these two bodies are in thermal equilibrium. Remember the definition of equilibrium that I mentioned last week. These two bodies are in equilibrium, are in thermal equilibrium with another body, a third body. Okay, if this iron and copper are in thermal equilibrium with a third body, means that they are also in equilibrium with each other. Okay, so second point. Okay, maybe second point is better explained. Means that by replacing the third body with a thermometer, example, if we have a thermometer, we put inside the the container here. We put thermometer, sorry. Thermometer here. Okay, thermometer here. Okay, so this thermometer will become the third body. Okay, by replacing the third body with a thermometer, the zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. Okay, so look at here. Initially, it was iron at 150 degrees Celsius and copper at 20 degrees Celsius. Now, when they become equilibrium, okay, those temperature, the temperature of iron and copper become will be the same. Okay, same temperature reading. Okay, it reach when those material iron and copper are in thermal equilibrium, they reach the same temperature reading. Okay. Next, temperature scales. Okay, this one I think you know. You have ice point, a mixture of ice and water. That is in equilibrium with air saturated with vapor at 1 atmosphere pressure. Okay, so ice point is at the 0 degrees Celsius or 32 Fahrenheit, but we usually use degrees Celsius. Steam point. Okay, steam is a mixture of liquid and water vapor. Okay, at 100 degrees Celsius evaporation. And then we have Celsius scale in SI units. Fahrenheit is in English unit. Thermodynamic temperature scale. Temperature scale that is independent of the properties of any substance. Okay, it doesn't depend whether the properties is in the substance is in liquid, gas, or solid. And then Kelvin scale, Rankine scale. Okay, so Kelvin is the SI units also other than Celsius. Okay, so this one tak apa lah. Ini tak. Just some definition, so it's okay. Okay, so look at here. This one, the reference temperature in the original Kelvin scale was the ice point. So 0 degrees Celsius equals equivalent to 273 Kelvin. Okay, which is the temperature of the ice. Okay, when the ice starts to melt. Okay, if we increase the temperature from 0 degrees Celsius to higher, so the ice will start to melt at the melting point. Okay. Okay, the reference point was changed to a much more precisely reproducible point, the triple point of water. Actually, this triple point is, there is a graph, a schematic graph that like this. So these points, okay, this is what we call a triple point, because outside of this point, we have liquid, vapor, and solid. Okay, so the this is like a diagram. I think we will see this diagram in future. So the point at the this location, if the liquid is at this point, it this is what we call the triple point. Okay, reference point. Okay. Okay, so this slide just want to explain to you the first how we transform from one scale to another scale. For example, from degrees Celsius to Kelvin. So you have to change this one. I think you have to remember by heart. Okay, how to change degrees Celsius to Kelvin? Just plus add 273 Celsius. Okay. And then next, international temperature scale. Okay, this one can skip, just some facts, information. Okay, pressure. Okay, pressure, a normal force exerted by a fluid per unit area. So for pressure, actually, the definition of pressure, okay, F over A. So pressure is equal to force over area. So means that a pressure depends on the force and it depends on the area. Okay, if we increase area, then the pressure will change. Okay, so this pressure is noted in Pascal unit or Newton per meter square. This is Newton, this is area meter square. Okay. So example, this man here, okay, we have two men, one at 150 pounds. So we assume that their area of feet is the same, 50 inch square. Okay, so their pressure, okay, the pressure produced exerted by them are different because the force or their weight are different. Okay, so heavier person, a heavier man will produce, okay, a higher pressure, okay, because it depends on their weight. Weight is a types of force. Okay. Okay, next. So, okay, we also have this definition of pressure: absolute pressure, gauge pressure, and vacuum pressure. So you have to know this definition. Okay. So this definition is also be explained in this graphic figure here. So maybe it's better to understand. Okay, when it's explained in figures like this. Okay. So gauge is the difference between the absolute pressure and the local atmospheric pressure. Okay, absolute pressure means that if we have if we are given the gauge pressure, so we can calculate, we can resolve the absolute pressure by adding it with atmospheric pressure. Okay. And vacuum pressure are pressure below atmospheric pressure. Okay, so these are the equation. Okay, so you can just apply this equation to, because normally we just want to calculate this and this. We want to know this. Okay, and this atmosphere pressure is basically given in literature. Absolute pressure is the one that you will want to measure. Okay, variation of pressure with depth. These are the ones that I mentioned just now, that maybe related to fluid mechanics. Okay, so you have the change of depth, kedalaman, depth will affect the change of pressure. Okay, so this are the formula. Okay, the absolute the pressure that we want to measure. So we have to consider the atmosphere pressure plus the height, the gauge pressure, rho gh, which is written as rho gh. Okay, so we also have a variation of density like this. You can use integral form. And then, okay, I think this one you can, okay, at different point of in the in the water depth, okay, at different point, okay, A, B, C, D, E, etc. So even though the surface, okay, is different, depends on the slope, horizontal, vertical, more horizontal, more vertical, etc. But the point here is that the height h, okay, the height from the surface of the water to the bottom level at point A, B, C, D. If the bottom level is the same, as long as the h is the same, so the pressure at those point A, B, C, D, E, etc. will actually be the same, because we only focus on the atmosphere pressure at the surface plus rho gh. Rho g is constant, and then h, the level. So as long as we have the same level of h, even though the surface is different, okay, but the pressure at those point A, B, C, D, etc. is the same, because the level of the h, the pressure gauge, are the same. Okay. Pascal law. Okay, this is the Pascal law just now. The pressure applied to a confined fluid increase the pressure throughout by the same amount. Okay. So, um, It means here, okay, for example, because we have this rule, okay, when Pascal law said the pressure applied to a confined fluid, for example like this, a confined fluid tertutup, okay, increase the pressure throughout by the same amount. So P1 equals to P2. If we apply P1 pressure here, so P2, the amount of pressure uplift uplift here will be the same as the amount of pressure that we apply at point 1, okay, because it is in a confined space or confined fluid here, okay. So the amount that we apply here uh, will be pushed to this at this side, okay, and push uplift the whatever we want to lift, okay. So this concept is being applied, for example, for this device, hydraulic jack, okay? And then barometer, okay? Okay, barometer, pressure is one type of device used to measure the pressure, okay, barometer. So atmospheric pressure is measured by a device called a barometer. Thus, the atmospheric pressure is often referred to as the barometric pressure. Okay, so we can use this barometer to calculate, to measure the pressure at a certain point in the fluid. Okay. 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 These are the application. Okay. So this is the interesting part here. The length or the cross-sectional area A1, A2, A3 here is different area, right? The A1 is bigger than A2 and bigger than A3. But it says here the length or the cross-sectional area of the tube has no effect on the height of the fluid column of a barometer. So you see that it's same height. Okay. So whatever the area is, the height will be the same. No effect on the height, provided that the tube diameter is large enough to avoid surface tension. So we assume that the surface tension, the force from the surface is negligible or very small due to the diameter. Okay, but because actually this is the ideal case. Sometimes, even though the area is the cross sectional area are different, but the height of the fluid uh, will not be the same. Will be different also, because that depends on the surface tension. Okay, so by here in these figures, we assume that the diameter is large enough so that the surface tension is negligible. Oops, sorry. This one also very interesting. At high altitudes, a car engine generate less power and a person gets less oxygen because of the lower density of the air. Okay, another one type of device of a device to measure pressure, which is called manometer. Okay, is commonly used to measure small and moderate pressure difference. Okay, this one, manometer, you will see in your thermofluid lab. Okay, next semester you will do thermofluid lab, thermofluid, thermodynamic plus fluid mechanic. So you will see this manometer. You will use this manometer to measure the pressure of the fluid. Okay, you will apply the concept of Bernoulli, etc. So you use this one. A manometer contains one or more fluids such as mercury, water, alcohol, or oil. Okay, so you use another fluid. Okay, inside the tube to calculate the pressure of a gas or anything. Okay, so how do you measure that? So the formula is here, P2 for example. Okay, we want to measure the pressure of the gas inside the gas. Okay, inside here we want to measure here. Okay, so we assume that P atmosphere, this one is the P atmosphere here, plus rho GH, plus rho GH here, which is at P2. Okay, so P2 equals to P1. Okay, so we assume that this P2 equals to P1, so P1 will be the pressure of the gas. Okay, so we just measure because of the same level height, okay, the rules just now, so we can calculate, in order to calculate the pressure of the gas at P1, we can simply calculate pressure at point 2. E is the same, okay, because of the concept just now, okay, the height, this one, the height, ni banyak lah, tadi, this one, okay, this concept. Okay, sorry, saya dah skip pula. Okay, next, in stack up fluid layers at rest, the pressure change across each fluid layer of density and height is rho GH. So still rho GH, okay? So just plus, right? And then you get the pressure at the bottom one. So this one also, okay, P1, you want to calculate P2. P2, mana P2? P2 here, okay? So P2 here will be equals to P1 plus rho 1G here, okay, rho 1G A minus H, A plus H, okay, the total height. So it doesn't matter whether the path that you took is like this, etc. Okay, like this, the path, but it only depends on the vertical height, which is A plus H, okay. And then, okay, from 1 just now, 1 plus A plus H sini, here. And then, minus, okay, minus rho 2 GH, rho 2 GH. So, the height here, okay, rho 2 GH and minus rho 1 GA. Because rho 2, because of this is in red here is different fluid, so different density. Fluid number 2, density rho 2, and back rho 1. Okay, so it's like plus and then minus, minus. Okay, and then you get the pressure at point 2. Other pressure measurement device, okay, these are some of the, other than barometer just now and manometer, we also use this type of measurement device to measure the pressure, okay. The weight tester, okay. Okay, okay, and okay, enough finish about the pressure and temperature. Now I want to explain a bit about problem solving technique, okay, because in your second half of semester, I will introduce to you, I know you have to do assignment, right? Mini project assignment. So in your assignment, you have to somehow solve a problem, like a case studies problem, right? So this in thermodynamics, we have this like a flow of a problem solving technique for thermodynamics. Okay. Normally, we use this software that we call engineering equation solver, but this is just example software of thermodynamic software. So it's not compulsory to use this one. This is just example, so we can skip that. You can also just use MATLAB or Python, okay, to solve a thermodynamic problem case study. So step 1, we choose a problem statement. So that's why we need to do literature review. in order to find out what is the current situation and what is the problem, the current with the current technology, right? And then we sketch if we can, we sketch a schematic diagram, okay, of the problem, because in thermodynamic we always have to understand the process. Okay, so we sketch it in a diagram, a schematic diagram, the process of the thermodynamic process of the system, the system that we want to study, the case study. And then we have to make assumptions and approximations. Okay, like I mentioned in the first chapter, sometimes we have to consider that the flow is in equilibrium, even though in real situation it is not in equilibrium or quasi equilibrium. But we have to assume, make assumption, make hypothesis, right? We have to make hypothesis. We are scientists, so we have to make hypothesis, we have to make assumption, or we have to make some approximation. Because if we don't do this, it is nearly difficult or impossible to solve a certain problem, a certain case study. So we need, as a scientist, the researcher, we need sometimes to simplify our problem. So in order to simplify our problem, so that we can apply certain laws, certain principle equation, we need to make assumption, hypothesis, or we need to make approximation. Like just now, we assume that there is no surface tension, right? So that we assume the height is different. It is the same. Sorry. Okay. So we make assumption, even though in reality it's not real. It's not true. And the physical laws, what are the laws, the principle, the equation that we can apply to our problem? First law of thermodynamics, second law of thermodynamics, law of conservation, law of Newton, whatever law that you know. And what are those properties that you need, that we have and we need to define. For example, we have information on temperature, we have information on pressure, we have information on mass flow rate, but we need to calculate the performance, the efficiency, the energy, the work, whatever, the force, right? Okay, so we have to define which properties that we already have, and which property that we don't have that we have to assume, and which properties that we have to calculate. Okay, so we do calculation. Okay, calculation, and we find our results, and lastly we verify our result and discuss whether it's true or near the truth, or what. So we analyze. So that is the most important part. Maybe we do not achieve the exact amount, the real results, but that is what scientists do. We maybe there is some errors in our results, but that's why we need to analyze, we need to discuss how much our error, how much is our error. Maybe only 10%. If our errors is only less than 10%, we means that we can accept, we can accept our answers. Okay, 10% is enough. Okay, but not higher than that. Okay, if the error is too big, means that we have to recalculate, redo, or make another assumption, other assumption. Okay, example. Okay, so this is an example. So that's why the easy way is to climb bit by bit, okay, instead of directly want to solve the solution. Okay, this is just example. So the word processing. A remark on significant digits. Okay, okay. As an engineer, these significant digits is very important. Okay, so please take this into consideration. Okay, so in your calculation, in your research, in your exercise, for example, case study, when you do your report, or when you do your lab, you need to only maybe rounding your answers to 3 or 4 significant digits. Okay, not too big. Sometimes students put answers like this: 3.25678 9. Right, it's too long and it's not neat. Yeah. So you have to simplify rounding. Your bundarkan your answers to 3 or 4 significant digits. Okay. It's not in as engineer, we cannot just leave our results like this. 3.25678 9 10. Panjang sangat. Okay, it's too long. Only 3 to 4 significant digits. That is how you report your results. Okay. So I have I have 2 exercise example. Maybe I will explain the first one, and the second one you can try to do by yourself. So I give answers here. Okay, so you can try by yourself. I will show only the first one. Okay. Okay, so first one, wait. First one is okay, on manometer. Okay. So we see a manometer is used to measure the pressure in a tank. The fluid used has a specific gravity of 0.85 and the manometer column height is 55 centimeter. If the local atmospheric pressure is 96 kilopascal, determine the absolute pressure within the tank. Take the standard density of water to be 1000 kilogram per meter cube. Okay. Okay, manometer. Okay. If we look back your manometer just now, this manometer, okay, like this one, at figure 1.55. Okay. Okay, go back to your exercise. Okay, so first one, what do we have to do? Okay, what do we have to do first? First thing is very simple. Okay, so it says here specific gravity of 0.85. The density of water is 1000 kilogram per meter cube. Okay, so first, we calculate first the density of the fluid. Okay, manometer is used to measure the pressure in the fluid. It doesn't specify here which type of fluid. Okay, so you just calculate the density of the fluid. Okay, so density. So you take the specific gravity. Okay, this is specific gravity Sg, and multiply with the density of water H2O given here. Okay, so like this, so you get the density of the fluid or this fluid. Okay, multiply 1000. Okay, so you have 850 kilogram per meter cube. And then, okay, from the figure of manometer just now, we know that the formula P is P atmosphere plus rho GH, right? Okay. So the atmospheric pressure is given here 96 kilopascal. So 96 plus rho GH. So rho GH, rho is the one that we calculate here, which is we get 150. G, the acceleration, we took 9.81 and multiply with H, the height. The height given here is 55 centimeter. So we use meter, the SI unit, which is 0.55 meter. Okay, so you get the answer. Okay, so you get the answer, the pressure, which is 100.6 kilopascal. Okay, or 100. You can also write down in pascal, whatever. Okay, pascal or kilopascal. Okay, so that's all. Okay, so that's all. You can try the next as one, exercise 2, 130 kilopascal. Okay, by using manometer also. Okay, so you can try this one. Okay, sekejap. I think this one I need to draw because I don't have photo. because you need to know where is the location of H1, H2, H3, right? So I draw a bit. Sorry kalau tak cantik. So it's like this. So you have air here and you have water here. Okay. So yang ni. Sorry. Alah. Susah pakai. Saya nak buat lubang sikit kat sini Okay. So this one. Kind of like this. So this is H1. Okay, this is H2. Inside is oil. And this is point 2. The middle here, so point 2. Nanti ni the same, same level. You have H3. So H3 is a bit higher than H2. Okay, this one at this level. Okay. So this is mercury. Okay, from here until here, this is mercury. Okay, all of this are mercury. This one from here is oil. Ini oil. See what you this is oil from H1 until level of H2, H3 here. Okay. Maybe better if I guna color lah kan. I use colors, different colors. So this is oil. This is oil. This is oil. This is mercury. Mercury. Okay. Mercury. And you have water here. Water bawah ni. Ini semua water. Ini air. Okay, this is water until here. Okay, try to solve that one. Okay. Okay. Okay, I think this is my last slide. Okay, so I hope you try this example. I think it's not too hard, insyaAllah. So anything you can ask me. So the answer is given here, 130 kilopascal. Okay. Okay, that's all from me. Thank you very much. Bye-bye.